Hi, in this video we'll be continuing our journey into probability. We are following the textbook by Sheldon Ross, first course in probability, and after going through all the continuous random variable and discrete random variable, we want to ask ourselves now that what happens when a probability is dealing with two or more random variables, and how are these random variables related to one another. And so let's take the case for two random variables. What we would like to define is known as the joint cumulative probability distribution. And that is really saying what is the probability that x is less than or equals to a and y is less than or equals to b. And so this is the definition of a joint CDF. Now, for the case of a discrete random variable, where both x and y are discrete, it means that the joint PMF can be defined naturally as the probability x equals to x, comma, y equals to y. And if you were to sum over all y's and all x, this probability has to equals to 1. And so, let's say we want to find the probability mass function of x only. We can obtain it from taking the joint probability mass function y with y. So is this, but now we sum over all y so that you only get the probability of x occurring for a specific value of x. And so really we're just taking probability of the union of all the y's of this event, and really that reduces to the sum of probability x equals to x and y equals to yj. And this is then the joint PMF. And so when we get the following probability mass function of x, when we know there's two or more random variables, we shall call it the marginal probability. And similarly, the marginal probability for y can be obtained by summing over all x's for a fixed y. I'll illustrate this with the table for you to better understand it. So for example, now we have the event that x can equals to 1, or the event that x can equals 0, y can equals to 1, and y can equals to 0. And the probabilities are given over here. And so this table represents a joint probability mass function for each of the event. And so the marginal probability where x equals to 1, you have to sum the case. So it's like case 1, y equals to 1, and case 2, y equals to 0. And so the marginal probability is 25 over 100. And really that's what it means to get the marginal probability distribution from the joint probability distribution. And so we can also ask ourselves, what is a conditional distribution? Since we know what are the marginal and the joint, we can ask ourselves what can be called the following probability over here. And that's really the probability x equals to 1 given y equals to 1. And so the conditional distribution can be defined naturally to be the PMF, the joint PMF over the marginal of x. And so the joint PMF is equals to the conditional distribution multiplied by the marginal distribution. And if you understand this table, you will understand why. And so everything we know about the discrete random variable that we went through, everything applies, but we now change all the summations to integrals to get the C for continuous random variables. And so the continuous random variables, instead of joint probability mass function, we have now joint probability density function for the continuous random variable case. And so when we say to sum over all x and sum over all y's, what we're really doing is integrating the possible values of x let's say x takes in an interval from A, and now y takes an event in B. Y can occur in the interval B. And so you're just integrating with respect to this area, which this area A cross B is the event that it occurs. And so you just need to integrate A and integrate B. And really, this means that the joint CDF is just an integration of the PDF from minus infinity to A for dx and integrate from minus infinity to B for dy. And if x and y are jointly continuous, meaning there exists a joint PDF, they are also marginally continuous. Marginally also refers to the individually here. And so if you want to find the marginal PDF for x, what you just need to do is you integrate the joint PDF with respect to y. So in this case, this is the CDF lah. And so the marginal PDF equals to the integral of the joint with respect to y. So it's like taking the sum of all the y's. Likewise for the marginal for y, you just take the integral with respect to x, because you want to sum over all x. And for conditional distribution, it also follows like the discrete case where the joint PDF is above divided by the marginal PDF. And really this table summarizes the similarities and what is joint, marginal and conditional for both the discrete random variable case and the continuous random variable case. And you can really see that in discrete we have summations, while in continuous we really have integrals. And two discrete random variables are independent if px equals to x, comma y equals to y equals to probability x equals to x times the probability y equals to y. And you can really think of it as this is the event A occurs and this is the event B occurs. If A and B are independent, it's the probability A occurs times the probability B occurs. Similarly for the continuous case. And so let's take a look at the examples to better understand how we deal with joint distributions. And so we have a joint density function of x between x and y given as follows. And so we want to compute the probability that x is greater than 1, comma y less than 1. And so that really you're taking the joint PDF and let's do the integration with respect to x first, so it's 1 to infinity, and the one with respect to y is from 0 to 1 because y is between 0 to infinity. And when you do the integration, you're just doing a regular two variable integration, which you can take a course on multivariable calculus to familiarize yourself with. But really you're just integrating the inside first and then you integrate the outside with respect to y. And you get the following result. For part B, you just need to integrate in the event that x is less than y. So it's really drawing the graph and this is the line y equals to x. So x is less than y means that is in this shaded region. And so what you want to do is integrate from with respect to x from 0 to y, and then with respect to y from 0 to infinity. So really this portion is really testing your ability to understand multivariable calculus, and you can really, once you get that point, all this integration with two variables will become very simple. And so we can really find the marginal PDF of x as follows. So we just need to integrate the joint distribution with respect to y. And we see that the marginal PDF is e to the power of minus x. Or we can find the CDF over here and just differentiate. It will result in the same conclusion. And so I've come to the end of this video, and I hope you have understand and appreciated why we study about joint distributions. We'll be covering more about properties of joint distributions in the next video, so stay tuned to understand more about joint probability distributions. Thank you for listening, and please feel free to like, share, and subscribe, and I'll catch you in the next video. Bye!